So today, fluids review, but first, a little bit about what Onshape can do. So I thought I would begin with just a few views of Onshape so that you can make sure that you understand what it is that we're looking at, and then I'll take you into Onshape for just a little bit of a tour. So this is a preview of a water treatment plant that's designed for, well, where this code can handle flows between about 10 liters per second and 80 liters per second. So by just changing one number, this entire design will change. Unfortunately, I can't just show you that because it takes a couple minutes for it to refresh when you change the flow rate. And so it's not fun to sit there and wait 2 minutes and wait for the design to change, but trust me, it does eventually update. So I would take a guess. This was for a 30 liter per second plant. This would be a plant that would serve something like 10,000 people, perhaps. And the scale, you should be complaining because there's no scale in this image anywhere, but the length here that I'm tracing with my cursor for this tank is, I'm guessing, about 7 meters. Okay. To give you a little bit of a sense of scale. And yeah, I tend to go metric the whole time. I know that you know metric and you maybe are more familiar with using English, but this is one of the ironies. I've been always very interested in going metric because it's just so much easier to design things in metric. And then we go and work in countries where, you know, our view is that everyone on the planet uses metric. And then you discover when you walk in that, well, actually, yeah, they use metric, but they also use English, and they also have another set of units that they use locally. And so it gets confusing. And it seems like we managed to pick countries to work in where the English units are still a holdover, both in India and in Honduras. And I've also been connecting a little bit with Guatemala, and the same thing is true there. So you're very much like all the other folks that I'm working with, that the English units are still hanging around. Okay, so we're looking at this plant. We're looking at a top view here, an end view, and then the isometric view. And then let's go in and look at individual pieces. So there's the top view of the plant, and that plant has many subcomponents. So the first one I'll pull out is the entrance tank. And the entrance tank, if we open up the side, it looks like this. So you can see the internals in that tank. The water is entering right here, flowing across the entrance tank, and then exiting through this linear flow orifice meter that we will learn about not too long from now. And then exiting down through this pipe where it then enters into the bottom of the flocculator. So here's the entrance tank, flocculator right next to it. So the next piece is the flocculator. The flocculator, the water has to go up and down, 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 and go through many expansions and contractions and generate lots of turbulence and ultimately generate lots of collisions between particles. From there, it passes into the sedimentation tank. The sedimentation tank, in this case, has, well, that's funny. Here there are 4 bays, and up here there were 5. So if you're counting, you're like, whoops, Monroe got this from 2 different designs. But don't worry, I'm just showing you how this works. And the point is, I can so easily change how many sed tanks or how many units are part of one of these sedimentation tanks by changing the flow rate. So the water enters each of those sedimentation tanks or goes through them in parallel. It goes through, in this case, one of these 4. And if we open that up, you can see that there's lots of good stuff happening inside that sedimentation tank. And we'll have a whole set of notes, a whole set of talks about how sedimentation tanks work. And then the last big process is the stacked rapid sand filter. And that is a complicated mess with lots of pipes and hydraulic controls that make it all happen. So you can see inside the filter box to see that there are tons of pipes inside the filter box. Okay, so we're able to change the flow rate at the very top level and have all of these subcomponents update correctly and redesign themselves with that new flow rate. And I wanted to just illustrate what needs to be happening there. So way up high in our, for the plant design, up on the left-hand upper corner of our screen, and I'll show you where this is at, there's a place where we can enter what we call overrides. And that's where we can enter in the flow rate. And when that flow rate gets entered in, it then is passed through code down to each of the subunits so that they get designed to be the right size as well. So the parent passes the information down to the children, and that notion of parent passing down to children actually happens at multiple levels within our designs. There are a parent who passes down to a child, who has a child, who has a child, and I'm not sure how far that goes, but it at least goes like 4 levels, maybe even further. And all the way down, it's possible to pass down whatever information is needed so that when it all comes back together, it all fits and we have a plant layout that makes sense. So with that, I'm gonna break from that, and I'm going to switch to this. So now you're seeing the plant in 3D, and I can rotate this around, and you can see that there's a lot of stuff going on. There are lots and lots of pipes, and we can take a peek into one of these, just like I did before, where I can hide an element, I think. Okay, and we can look inside a tank and see what's in there, and there's a lot of pieces going on. So that was the entrance tank. We can look down, and in this particular design, I have turned off, up here in my inputs, I've turned off replication. I made replication equal to false, and I did that. Replication equals true would like replicate all of the duplicated parts as many times as are actually needed. So for example, if you look into this tank right now, you'll see that the flocculator, there's only 2 pieces of plastic here making the little baffles, and all the rest of them aren't drawn. That's because I have rep set to false, and I do that so that I can move around here and show you things quickly, because it starts to get slow as we start making all these pieces show up. I want to talk a little bit about how Onshape works. So Onshape, ultimately everything in Onshape is computer code. You can either create drawings directly by writing feature script code, or you can create them using this feature list, which is on the left-hand side of the screen. In either case, it's created using code. And all this feature list is it's a nice graphical representation of a set of functions that are being executed. So remember that execution happens from the top of this left-hand panel down through. And if you want to make it stop prematurely, you can drag this bar, and I'm not going to do it because it takes a long time for this to reload. You can drag that bar back to wherever you want to stop the execution, and it'll stop at that point, and then you can edit it at that point if you'd like. So execution happens from the top to bottom. This is all just computer code, but with some nice interfaces that make it easy for you to create new objects. And you'll notice here that this is then the code that is used to create this whole plant, which seems like we're cheating, and we are, because you can see very clearly there's some code up here called plant, and then there's the sedimenter, and then there's a flocculator, and then there's a a port between the flocculator and the sedimentation tank, and then there's an entrance tank, and then there's a filter. So you can see that pieces of code that are bringing each part in. What's maybe cheating is that each of those pieces of code has a whole lot going on inside it. They're complicated modules. So that was that. And I wanted to point out that, okay, here's where the flow rate is input. If I were to change that, everything would change. If I would type in 30 there, it would redesign this plant for 30 liters per second. Okay, and maybe in the interest of full disclosure, one of the challenges that we have is that we're essentially adding some more capabilities to Onshape than what they were originally intending. And our method of passing information between layers is something that we invented. And it was difficult for us to be able to pass numbers with units between layers. And as you will find out as you work with me, I think it's super important to, when we're designing things, to design using numbers with units and to have the numbers with units go through our design process. So FeatureScript normally handles units just fine. It's just that we have this little issue of the way we needed to pass information between parent and child. That didn't work out fine to handle units. And so you'll see here that my number 20 doesn't have units on it. And man, this is a little messier than what I was intending to get into today, but the way we handled that is we have code that looks at the variable name, and we have very precise naming conventions for our variables, so that just by looking at the variable, you know what the units have to be. So a variable with the name capital Q in it has to be a flow rate, and then the M after that Q stands for milli. So this is milli flow rate. So the default units for flow rate would be cubic meters per second, because it's just standard SI units. And then a milli of a cubic meter is a liter. So QM gives you liters per second. So I can enter 20 in there, and that gets processed into code as 20 liters per second. Matter of fact, I should be able to come over here, and now I've pulled up the variables that are defined in this code. And there's QM max, and it has a value of 0.02 cubic meters per second. So we processed it. It's got its units attached to it. It's 20 liters per second. There are also, and I'm realizing you're not a computer science group, so I am not sure how to talk about this. There's a map, which is a list of variables that are defined for each subunit. So for example, up here is entrance tank, and here is a list of variables, and that list goes on, and we can't see nearly all of them. But you can see that, for example, here's FB, which is our freeboard of 10 centimeters. There's a length of the entrance tank. There's now another list of variables related to a linear flow orifice meter. So all this information is packed in here, and there's ways to access that if you need it as you're continuing on in the design. And what I'm showing you here, in case you're worried that you're going to have to create this tomorrow for an assignment and it's not going to look good, don't worry. You're not going to be creating anything this complicated over this course, although you will get to play with some of this. We'll work at building this up so that you're comfortable and you're starting with something simpler and you see how it works. Okay, so those are a bunch of variables. And then one more thing that I wanted to show here is that we have a bill of materials. So this bill of materials is the list of all the parts that are in this whole plant, and it includes their prices and the quantities. And I've added this recently. There's also a cost that is the total cost for this project for the materials is $50,000, okay? And then the the cost per liter per second is sort of a measure of the efficiency of this design. Like how much does it cost for every liter per second of capacity that this plant can deliver? And you can see here, we calculated it to be basically $2,500 for every liter per second of capacity. Our experience is that by the time you actually build a plant and you include all the labor and all the design work, the costs for building a liter per second of capacity exceed $10,000. So this is a fraction of that, because this is only the material cost, and maybe not, well, this does not yet include all of the material costs because it's still missing a building that goes around this whole plant. There's also a cut list, and I want to just show you that even though we don't have every plate settler drawn in this plant, they all are here. So here's the list of polycarbonate sheets that are 0.5 meter long, and there are 604 of them. So there are actually 604 plate settlers in this plant. Even though they're not all drawn, the software knows about them and has kept track of them.